Hello guys, how are all of you? I am Vidya and I welcome you all to my channel Extremely Easy. My today's topic of discussion is Euler's theorem. Now, if I ask you a question, how would you compute 2 raised to 1000 mod 7? Extremely easy, isn't it? Since 7 is a prime number and since 2 is not divisible by 7, your immediate reply would be we would apply Fermat's theorem and we'll solve 2 raised to 1000 mod 7 in steps by replacing 2 raised to 6 mod 7 as 1. We have solved this particular numerical in the previous video. The link is provided in this video. Now, my question to you is, I want to compute 2 raised to 1000 mod 15. So, can we apply Fermat's theorem for this question? Definitely not, because 15 is not a prime number. 15 is a composite number. So, what is the solution? So, this is what we are going to learn in Euler's theorem. Euler's theorem allows us to solve numericals of the kind a raised to x mod p, where a and p are any positive integers. Moreover, p can be a prime number, it can be a composite number, it can be raised to the power of prime number, so p can be any number. The only condition is that a and p should be relatively prime numbers. So I request you to view this video till the end, and I am sure that you will be able to easily solve any given question on modular exponentiation very quickly using Euler's theorem. So let us now move on to our computer screen and understand what is Euler's theorem. Let us now see what is Euler's theorem. So if we have two positive integers a and p, that is if a and p are positive integers and are relatively prime numbers. What do you mean by relatively prime numbers? It means that the greatest common divisor of a and p is equal to 1. So if this condition is satisfied, in that case we can replace a raised to power of phi of p mod p with 1. That is, a of phi p mod p is congruent to 2. So it means that if we get a modular exponentiation question of the kind a raised to phi p mod p, we need not compute it using a squaring method. We can directly replace the answer with 1. Now what is phi p? Phi p is known as Euler's Totient of p. Let us now see how to compute Euler's Totient. I have explained Euler's Totient and its numericals in detail in one of my videos, the link of which is provided in the right hand corner. However, I'll quickly revise it here again. Euler's Totient of any number p is represented as phi of p. Now, p can either be a prime number, p can be a composite number, and p can be a power of prime number. So let us see what are these three types of number. Prime number is the number which is divisible by 1 or itself. What is a composite number? Composite number is a number which is a product of two prime numbers. So it can be written as x into y, where x and y are prime numbers. Now what is power of prime number? That means p is again not a prime number, but it can be represented as power of prime number. So if x is a prime number, p can be represented as x raised to power of e. So in this case, x is a prime number. Now depending upon whether the number is prime, composite or power of prime number, we use different formula for Euler Totient. Now let us see the formula for Euler Totient. If p is a prime number, the Euler Totient of a prime number p is given as p minus 1. If p is a composite number, that is, p can be represented as product of two prime numbers x and y. In that case, the Euler Totient of a composite number p is given as x minus 1 into y minus 1. While if p is a power of prime number, that is, p is represented as x raised to power of e, where x is prime. In that case, the Euler Totient of such kind of number p is given as x raised to power of e minus x raised to power of e minus 1. So these are the three formulas to compute Euler Totient. So when you solve numericals on Euler theorem, the first step is you should be able to identify if the number p is prime or composite or power of prime number, so that you can use the appropriate formula of Euler Totient. Once you have computed the Euler Totient, then you can easily use it in Euler theorem and say that any number a raised to the power of the Euler Totient of p mod p can be replaced or is equivalent to 1. So rather than computing a raised to phi p mod p, you can replace the answer directly with 1. there is no need of computing this answer using squaring method or by any other method, because the GCD between a comma p is equal to 1. You can replace a raised to 5p mod p as 1. And this is known as Euler's theorem. So this is the entire crux of Euler's theorem. So what are the steps used to solve numericals using Euler's theorem? So to apply Euler's theorem, first and foremost, the question will be a modular exponentiation question of the kind a raised to x mod p. So once you know the value of a and p, the first step is to check if a and p are relatively prime numbers, because only and only if they are relatively prime numbers, then and then you can apply Euler's theorem. Now what do you mean by relatively prime? It means that the GCD of a and p should be equal to 1. So if this condition is satisfied, we can go to step 2. If it is not satisfied, we cannot apply Euler's theorem. So you can conclude that we cannot apply Euler's theorem. So now if this condition is satisfied, we go to step 2. In step 2, you have to check if p is a prime number, or is it a composite, or is it power of prime number. So once you have identified whether it is a prime number or a composite number or power of prime number, you can apply the appropriate formula of Euler's Totient. That is, if p is prime number, the formula goes phi of p is p minus 1. If p is composite number, which is a product of two prime numbers x and y, then the Euler's Totient goes as phi of p is x minus 1 into y minus 1. And if p is a power of prime number, that is of the kind x raised to power of e, where x is a prime number, in that case the Euler Totient of p is given as x raised to e minus x raised to e minus 1. So once we have finished with the second step, we can then move on to the third step, where a raised to the power of 5p mod p can be replaced with 1. That is, in step 3, we use our main Euler's theorem and replace a raised to 5p mod p as 1. So with these 3 steps, you can solve any given question of the kind a raised to x mod p, where x is nothing but it is the value of the Euler Totient. So if x is equal to the value of Euler Totient given in the question, then a raised to x mod p becomes equal to 1. If you see these 3 questions, the 3 questions are of the kind a raised to x mod p. That is, these questions are called as questions of modular exponentiation. Now, if you want to solve this question, there are 3 ways you can do it. The first way is called as the traditional method by squaring. However, the traditional method by squaring is computationally intensive or lengthy, as you have more steps to solve in this case. However, to make the computation faster, you can use 2 methods. The first one is using Fermat's theorem. However, Fermat's theorem is restricted only to the modulus of prime numbers, and the second method is Euler's theorem, where p can be any positive integer. So in Euler's theorem, there is no restriction on p. While in Fermat's theorem, you have a restriction on p, that is, p should be a prime number. Therefore, if you want to compute a raised to power of x mod p faster, you can go for Fermat's theorem or Euler's theorem. Euler's theorem allows you to have p as a prime number, p as composite number, or p as power of prime number. So you can easily solve any given modular exponentiation question using Euler's theorem, and which is a faster method as compared to that of the traditional squaring method. So that is the basic significance of using Euler's theorem. So we have come to the end of today's video. I hope you all understood the concept of Euler's theorem. Kindly let me know in the comment section. Also, in my next video, I am going to solve numericals on modular exponentiation. I will provide you with the step-by-step guidance to solve the same, and you can solve all these questions very easily using Euler's theorem. So thank you guys. Thank you for watching my video. See you in my next video. Stay happy, stay healthy, stay blessed.